Hello all, I welcome you all to the 22nd lecture, this course EE614. The last time we met, we spoke about MOSFET. We had a very mild introduction. We saw about the various versions of MOSFET, the NMOS, PMOS, MOSFET meaning the metal oxide field effect transistor. We saw the basic structure, and then we understood that the MOSFET is basically a 3D device. So we have, I'm going to try and draw the cross section here. So we take a bulk silicon and we deposit on top of it a gate oxide. Right, so this is the gate oxide, and on top of this we make the gate contact. And for our current discussion today, where we will discuss about current conduction, the equilibrium structure in the MOSFET, we are going to consider this particular part where we have a region in the PMOS which is heavily doped. We have another region similarly heavily doped, which we are going to call the source, and the other one to be drain. I'm sure you must have seen this particular structure sometime before, but we will currently deal a little bit more in depth in understanding how the MOSFET works, what happens to the charge, what happens to the current under various potential biases, and finally we will stop with some introduction to the situation when we have velocity saturation and such. There is a complete detailed course on MOSFET, so we will not spend too much time on understanding. I mean, we will deal with the most basic principles of MOSFET, but we will not go into much further detail into the characteristics and such. Okay, so with this mild introduction and with this structure in our mind, let us look at what happens in the material when you apply bias. So for that, let us first look at the equilibrium band structure. So again, I'm going to repeat. So basically, this is a p-type semiconductor. We have a gate insulator, which is silicon dioxide, on top of which we have put a metal contact. And then we have N++ or N plus diffusion, which we call as source and drain contacts. For our practical purposes, let's assume that this width of diffusion is really large and it goes much deeper than most of the important features that happens below the gate. Okay, so under these pretenses, let us look at the structure, and I'm going to draw the band structure with an additional dimension. Typically we do it in a two-dimensional space with the energy across potential, potential across just x-axis, but here we have to draw the potential across x and y-axis. So the N plus region is something like this. You have an the intrinsic layer. I'm sorry, so I'm going to we have a source side, and now we have the channel is now PMOS, right? So it's this area I'm talking about. So you have a PN junction, so you have a slight raise as we can expect, and we have another N type here. The device looks beautifully symmetric. We have a source, we have a channel region which is right below the gate, and we have a drain region. Now for our current discussion, we have to also draw the, so this is the x-axis, right? So typically we draw the potential V versus the x-axis for our typical band structure diagrams. That's what we have seen. But for understanding a MOSFET, you need another in-plane direction, which is y, because we are talking about some change in potential along this direction also, right? So this is our y, this is our x. So what we have to do is we have to draw this potential here as well. There will be a slight trace, right? Forgive my 3D drawing might not be very good. So it's something like, so remember, so it's a bulk of silicon that we're talking, and we are talking about this x and y plane, and the z is potential as we are talking, right? So don't think that the z is the thickness dimension. That's not we are talking. We assume the thickness is going to be uniform. So basically, so this is the x, y, z, right? The z plane, we don't assume things to change. It's still considered to be uniform across the gate direction. So remember, this is the width, right? So this is typically the width of the transistor, and this is the length of the transistor, right? So under these conditions, we know that, let's say it's n plus, right? So our Fermi level will look somewhat like this. Let me draw the Fermi level in a different color. So you have a heavily doped n plus contact. It's a bit p, it's p in the channel and the n plus in the drain. So this is the general situation at equilibrium, right? And there is no current and we have not applied any biases. So this is the standard situation. So let's assume that the source is connected to ground. The p-type semiconductor is connected to the ground, which is called as the body contact. And for our current discussion, the drain is also going to be connected to the ground, right? So now the second thing that we are going to see today, still at equilibrium, right? Let's assume Vg not equal to 0 and Vd equal to 0. So now I'm going to apply a potential and invert this p-type behavior. This is something that we saw in our metal oxide semiconductor treatment. So if it's a p-type semiconductor, we can apply a positive potential bias, and if the potential bias is more than a critical value, which is 2 psi b, we know that we can invert the channel, right? Which is, you start to have the onset of strong inversion. So when we have an onset of strong inversion, let's see how the band structure will look like, right? So once again, I want to remind you that this band structure, whatever that you see in the z axis, is not the thickness, but it is just the potential landscape. So now let me just draw this again. So it will look like this. We have a source, and so basically this is y, right? And at this particular point, it is the it's the surface, and when we invert the channel, you create an electron concentration at the surface, right? So the surface now becomes a little less p, but a little bit away. So a little bit away from the surface, it will again change. So I think so what we are trying to show here is that there is a dip in the potential in the channel, such that when I draw the Fermi level, I have an inversion at the surface. So once again, I'm drawing the so this is EF. At the surface, you have a slight dip in the potential space. So the conduction band in the p-type semiconductor has actually reduced a bit because of the applied potential, and you have the EI in the p-type semiconductor lower than the Fermi level. So you have an electron concentration at the surface of the silicon say insulator interface, right? So this is at equilibrium. Now let us consider what happens. So okay, so the EV EC, I suppose now this is clear, right? So this is how, and you have to remember that the Fermi level goes the same way everywhere, right? But then in the bulk of the semiconductor, the conduction band is still far away from the interface, and hence these regions still remain a P. So these regions is still a p-type semiconductor, right? You have an inversion only near the surface, so this is inverted, and this is the Y. So in this place we have an inversion here, and in a very small distance away from the surface you still have the normal p-type semiconductor with the conduction band as far away from the Fermi level as it should be for a normal p-type semiconductor, right? So with all these things now understood, now let's go to the third situation when we have Vg not equal to 0 and positive, and then Vd greater than 0. So I apply a positive potential at the drain. So if I apply a positive potential at the drain, it's easy to see that I'll have to reduce the Fermi level, right? So I have to reduce the Fermi level, but far away, let's say far away in the drain contact, the carrier concentration is not largely changed, right? So all the conduction band and valence band and the intrinsic levels, all of them are reduced as much as the applied drain potential. So let's look at how the band structure will look in the XY plane and in the potential surface if I apply a potential, if I apply a non-zero drain potential. So once again, the simplest source is still connected to the ground, nothing else changes in the source. So I have the EI, I have the conduction band, I have the valence band, even in the 3D space. Now because I have applied a positive potential to the drain, I have to have a very different, so okay, the Fermi level here will be somewhere here, right, which I have not. So now let us see, it should have been like this, but because of the fact that I have applied a drain potential at the drain side, the Fermi level is now lower, right? So I should have the drain Fermi level here, and this is QVD, this is the applied drain bias. So this is the quasi Fermi levels, right? So this is EFN, this is also EFN. Now let's take a look at what happens to the conduction and the valence band, and we know that the conduction and the valence band should still maintain the same separation as we had here. The EI should be here, right? So now the question is what happens in the intermediate regions, and because I have applied a positive potential to the N side and the base or the p-type semiconductor is grounded, you can clearly see that the base drain junction is going to be reverse biased. So when it is reverse biased, you have some you have this guy bending in this fashion, right? Right, so basically because of this applied bias, you have a reverse junction here. That is the base and the, I mean the body and the drain junction is reverse bias. But this forward potential, this drain potential that you have applied also makes that the channel being slightly positive in compared to the source. Hence this p channel source junction seems to be forward biased, right? Because I've applied a positive bias um, in the drain side. This positive potential has to have a small gradient, so the channel will be slightly more positive than the n side source. So your source channel junction will be positive biased, and hence you will have a smaller raise in the p type channel in comparison to the source, right? So the Fermi level here will have a slight slope and a stronger slope here, right? This stronger slope is because of the reverse bias junction. Substrate drain junction, and this mild positive slope is because forward biased source body junction, right? So if I draw the intrinsic level following the conduction and valence band levels, you can see that there are some regions very close to the base where the Fermi level has again gotten to be lower than the intrinsic level, right? So basically the actual inversion that was achieved by the gate bias that was applied before has now been lost because of the fact that you have uh, a drain potential which tends to deplete the drain body junction. So basically this particular region, this depletion region in the drain source, sorry, in the drain body junction, it gets depleted of the charge carriers, and hence your inversion is kind of lost near this drain junction. We will very shortly calculate these things in exact numbers. I'm just trying to give you the feel for what happens to the charge density at the source, at the drain substrate junction, right? So but again we have to remember that the deep in the body nothing much has really changed. So you will have a raise which falls down sharply. So these regions are deep in the body. Nothing much has changed. You still have a NPN junction, right? Which does not carry any potential. Close to the surface, you have a dip in the conduction band because of inversion. But then this dip becomes more and more less pronounced when we go closer to the drain, because the drain potential being negative, I mean positive drain potential applied at the positive drain potential makes the bands to bend, and you can have some regions in which the Fermi level is now higher than or lower than the intrinsic energy level, giving you a lesser inversion than you had in the channel closer to the source, right? So with this understanding of the band structure and the electron distribution in the source body drain junction, now let us try and calculate the exact currents in these junctions, right? So now we will make, as we did in the PN junction, let's make some assumptions. One is the gate oxide capacitor is ideal, in the sense there are no trap charges at the interface or in the bulk. But at the end of this lecture, we will also see that it can also be accounted for. But when we first start dealing with, we are going to assume that the gate oxide is ideal. Second, only drift currents will be considered. This is a very important assumption. So this assumption already tells you that we are not going to discuss current conduction when the surface is not inverted. So all the current conduction characteristics that we are going to talk now is when the surface is inverted. So basically only after the threshold, right? Because if you want to consider only drift current, that means that you have a very high carrier density, right? And such high carrier density is typically observed only when you have an inversion, right? So basically this is the second condition, which says that the current character IV characteristic we are talking about is above threshold. Sub threshold is something we will deal the next time. Okay, so the third thing is the doping in the channel is going to be assumed to be uniform. Fourth, the reverse leakage is negligible. Because the drain body junction is reverse bias, we do not want to have a whole injection into the drain and such. And fifth, another important point, which is called as the gradual channel approximation, which says that the lateral field is much larger than the transverse field, in the sense that if I take this surface, you have two kinds of fields. You have a field, okay, let's see here. When we have an inversion, right? So basically you have some carrier concentration here. So you have field from source to drain going here, right? And you also have some charge or some field from here to here in the y direction. So basically you have an electric field in the x direction, that is along the channel, and you have an electric field along the y. Why do you have an electric field along the y? Because of the fact that when we apply a drain bias, you have some potential in the channel and you have the body being grounded, right? So basically you have some potential difference between the body and the channel, which can cause the electrons to be drifted along the or away from the body, right? So we are going to assume that the lateral field is much larger than the transverse field, and hence this is called as a gradual channel approximation, right? So under these conditions, let us see if we can calculate the current. So it can be given by this expression. So basically the drain current is given by, let's say, W being the width of this. So we define this, right? So it is the width of the gate, and L being the length of the channel, width by length, integral 0 to uh, L Qn of y. Qn of y is the charge. So basically let's take something like this. So basically you have the charges in this region, right? Vy dy. So maybe I should use x here, following our previous discussions. Right? Because it is x is along the length. So we have some charge density at the surface which varies along the x, right? Because of the applied drain bias, the charge density is not uniform. If the drain bias is not there, then we can assume that the inversion is uniform across the channel. But because we have applied some drain potential, you have a charge which varies with between the distance from the source, right? And Vx is the velocity at each point, and the current should be a constant value. Current is conserved along the channel, right? So basically I'm talking something like this. This is the source, we have drain, and this is along y. And if I apply a gate bias, I have a charge density here which is a function of the x, and at each point x you have a velocity Vx, right? And because the current is constant, what we do is we integrate the charge from 0 to L and divide it by L to give you a value for what is the field of what is the average charge at any point. So the current is calculated by average charge at any point multiplied by the velocity to give you the actual current at that particular point, right? So this is the general equation for the drain current. So the question now is, how do you find the charge density Qn? There are different ways to find it. So now let us go over one by one. Methods to find Qn of x. So the most common method to find the Q1 of x is to solve the Poisson's equation, like we have previously seen how to do this, right? So how do we do it? Qn is q integral 0 to some x1 np, actually this has to be y1 np of y dy, right? Because we assume this direction to be y, and we say that you have charge depletion to some distance y1 from the surface, right? So you have the channel to be inverted up to some distance in the body, which is assumed to be y1. So we integrate 0 to y1 np of y. Np is the surface charge density and we know the equation of np, because this is something that we have derived in our previous metal oxide semiconductor junctions. How do we know what is that? So the majority carriers in the p-type semiconductor is equal to Na, that's the doping density, Ni square by Np naught. This is something that we know, right? And it can also be written as a function of Ex, which is P of x is Na e power minus beta psi p of y, right? Psi p is something that we have previously defined. Psi p is called we know that psi p is ei of infinity minus ei of y, right? It's a deviation of the by q. It is a deviation of the intrinsic energy level from the bulk and to the surface, right? So this is something that we have previously seen in the metal oxide semiconductor treatment. And NP of x is NP naught e power beta psi p, but here we also add beta Vd. Why? Vd is the drain potential, and as we have seen here, so this is Ei, and we know that this is psi p, right? And whatever this psi p is, it is added to the potential Vd that we have applied, right? So everything, so basically this is Vd, right? So your psi p is over and above the Vd, and it is written in this particular fashion. So with this given, we can substitute Qn, which is written as Q integral psi s to psi b, b being the potential in the body, s being the potential at the surface, Np naught e power beta psi p minus beta Vd d psi p by d psi p by dy, right? And from the Poisson's equation, you know that d square psi p by dx square is q by epsilon s Na minus p plus n, right? So Na is the ionized dopant density, because you know that the channel, when it is depleted, you have also some ionized acceptor ions which are negative, right? So Na minus p plus n is the actual charge density in the semiconductor, and we can integrate this, and this is something that we previously saw in the metal oxide semiconductor junction treatment as well. And you can find the surface potential the field E, which is minus d psi p by dx, which is an integration of this, which will turn out to be plus or minus root 2 kt by qld root of e power minus b psi p plus beta psi p minus 1, continuation of the root, Np naught by pp naught e power minus beta Vd e power beta psi p minus beta psi p e power beta Vd. The beta Veds are coming because we had an additional term Vd here, which was not there in our previous metal oxide semiconductor treatment. Now because we have this, we can have to integrate along with this, and you will get this. If you follow the previous discussion in metal oxide semiconductor, you can very easily see that this one falls down pretty easily from there. And this entire thing in the root is the f function as we previously used, beta psi p Vd Np naught by pp naught, right? So but then we see that this is something which we can only have to numerically solve. A simpler way can be to do a very simple approximation and then do a simplification. The approximation is, instead of assuming that you have a inversion layer of particular thickness y1, I'm going to assume that the inversion layer is a very thin sheet, which is called as a charge sheet model. Or an approximation. If we make this approximation, then the actual calculation of the charge becomes much simpler, right? So to do this, we write that the total charge in the semiconductor is summation of the charge of electrons in the interface plus the charge in the depletion width in the body, right? So we write it QB. And if we assume that WD is the depletion width, remember, if I apply a gate potential which is greater than Vt, you have a depletion width in the body in addition to, so basically here, right? if I apply a Vg here greater than Vt, it's not that I only have the electron channel here, right? So I also deplete the channel to some width Wd. So it is that I'm talking about. So this Wd is the depletion width when the channel is inverted, right? And this depletion width was calculated previously also. It is QNA Wd, which if the surface potential is written as surface potential at any point is written as delta psi I of x plus 2 psi b. Remember, 2 psi b is the potential that you have to apply to it's a potential that you have to apply to invert the channel, right? This is to invert the channel, and this psi I of x is the potential due to the applied drain bias, channel potential. Right, so you can see that this psi I will turn out to be opposite to the potential that is required to invert the channel, and hence you can see the surface potential will be lesser than the potential required to invert when psi I is close to Vd, which is the drain potential, right? So with this given, we can write that Qb is minus QNA Wd, and Wd is written as minus root 2q epsilon s Na delta psi I of x plus 2 psi b. So this is the surface potential. Once you know the surface potential, and we have assumed that the charge sheet is the inversion layer is a sheet, so it is at the surface, and hence you have from there on you have the depletion width, and once you know the potential at the surface, you can calculate what is the width of the depletion using this particular formula. This is something that we have derived even in our PN junction. Now, if we assume this to be the surface potential, now you can also calculate what is the charge on the metal, right? So basically, let's say you have this to be the gate, you have an oxide here, and you have a charge sheet here, right? So this is Qs. Now, because the entire thing should be charge neutral, right? So the actual charge Q, yes, which is same as the charge on the metal gate, is actually Vg minus V psi s, that is the surface potential, times Cox, which is written as Vg minus delta psi I of y plus 2 psi b Cox. This is Qs of y, right? So we know Qs of y, we know Qb from here, so you can actually calculate Qn of y is Qs of y minus Qb, and the actual charge, the sign of the charge is immaterial here, which will turn out to be Vg minus Vfb. So now we also account for the fact, let's do this later on, it's Vg minus del psi I of x minus 2 psi b Cox minus root of 2 epsilon s Qna del psi of x plus 2 psi b. I have made a few mistakes here. All of these guys should be x because x is something that I have taken it to be along the channel direction and y is along the width, right? So all of these things are x. And if I assume that now I'm going to lose one of the assumption that we did before, saying that uh, the metal semiconductor work function is non-zero, and the interface oxide charge density is also not zero. So basically I'm saying that the oxide need not be ideal. So under such situations you have VFB being the flat band voltage is psi ms plus Q oxide by C ox. So once I have something like this, I can actually write the exact charge density Vg minus VFB minus del psi I of x minus 2 psi b C ox minus 2 epsilon s q na psi I of, right? So this is the total charge due to the electrons at the surface, right? So maybe we can spend a minute to just to draw. So basically, if this is the surface and you have y going into the bulk in this direction, this is the surface, so you have qn charges at the surface and qb charges at the bulk, and this is minus qna and this is wd, right? And when I draw the when it is just when the drain potential is 0, then I have, and the gate, and it is just inverted, right? So the Fermi level is flat, and at the surface the Fermi level is above the intrinsic energy level, and you have an inversion here, right? This is the equilibrium condition. And when I apply the drain bias, I have something like this. This is where EI, far away from the surface. Once again, this is the surface. Far away from the surface, the conduction band and the valence bands are not really modified, and this is EI infinity, and the EI should also move along with the conduction and valence band, and the Fermi level is this EFP, and the EFN at the surface where you have an electron is here. And remember, this entire thing is the psi p at any point x, and at the surface it is written as psi s. right? And it is from here that we write this. Remember, so this is psi b, right? And it is from here that we write this relation, that the surface potential is del psi of I and delta psi I of x plus 2 psi b, because 2 psi b is this, and psi s, so if I so the Fermi level is above the intrinsic, so this is the intrinsic level. Fermi level is above the intrinsic level by 2 psi b, right? And the intrinsic level is as reduced from the original intrinsic level by the applied potential psi I of, or Vd, that's applied potential, right? So this is psi I of x. When x is equal to the drain, it's equal to Vd. So at Vd, your surface potential is equal to Vd plus 2 psi b, is as we can see from this particular plot, right? Great. So now that we know what is the charge, let's calculate the current. ID is W by L mu n. Wait, before we go here, we also do have one assumption. One is constant mobility assumption. Under this assumption, you assume that the velocity x is proportional to the applied electric field E along the x, and the proportionality constant is mu. Mu n is the electron mobility. We have seen this relationship before. If this relationship holds, and you know when this will break, right? When the velocity saturates, but that's something we will deal later today. But if the velocity has not saturated, this relationship holds, and we use our previous equation for the current, which was ID is W by L integral 0 to L Qn of y, again a y, Qn of x Vx dx, and Vx is written here, integral 0 to n Qn of x, and Vx is actually Ex mu n, so mu n, and Ex can be written as d by dx of del psi I of x, right? So this is the potential, right? Differential of the potential is the electric field into dx, and basically it will turn out to be an integration of the charge with respect to the potential. So W by L mu n 0 to Vd, because that's how the potential is going to change, right? 0 is the potential at the source and Vd is the potential at the drain, and Qn of del psi I d del psi I, correct? So if we go back to this, or not in this, now we have to look at the other side, right? Source and drain, and at any point in, so this is x, at any point here we call it the del psi of x, and the del psi of x is the potential, right? And the potential will drain like this, so this is del psi of x, and it changes from Vd at the drain to 0 at the source, and that's what we have written. And depending upon this del psi, you can see that the charge will also change. The charge will be exact opposite of the potential that we draw here, right? So basically you will have a charge which will look like this. Why? Because near to the drain you have a pinch off, so to speak, right? So if I substitute the charge from this equation, I get the actual expression for the drain current which is valid for all the regimes after the threshold. Why? Because we have assumed only drift currents. Cox Vg minus Vfb minus 2 psi b. Remember, the square roots that we have here led to this 3 by 2 things, right? And whatever that the constants here gave you this particular thing. So this particular term is to do with the charge density in the semiconductor, and this has to do with the charge at the interface. Right? And this is the entire expression for the current which we can use to decipher or understand the entire MOSFET output characteristics. And this expression is quite general and valid for all conditions above the threshold voltage. Right? So now let us look at the various regimes of operation of a MOSFET given this drain current characteristics. First is when Vd is very small. Right? When Vd is very small, you can see that in these two expressions, Vg minus Vfb minus 2 psi b is greater than Vd, right? And hence it can be much greater than Vd, right? So basically you will have a region which is linear in Vd, right? So basically your current will be now proportional to some constant times Vd, because you see that if Vd is small, the second term will also vanish, right? Because Vd plus 2 psi b is almost close to 2 psi b, so the second term will also vanish. The first term, the multiplicand is mostly dependent upon Vg, and hence you'll have a linear relationship with the drain current, right? So this is what is called as the constant linear current regime. The second easily understandable thing is when Vd is large. Right? When Vd is large enough, you can see that the you will have some region which becomes devoid of the charge at the interface, right? So basically you will see that this term can tend to 0 at some particular point, right? And hence the entire charge of the interface can become 0 at some point in the potential, right? You understand? Please remember that this Vd changes with the position in the channel, right? So there is no one particular Vd. So this is the gate potential, source and drain. Your Vd varies, whatever Vd that you apply varies with different points in the channel. So at very high Vds, you will have some regions in the channel where this term tends to be 0, and hence you have no charge at the interface. But then you will have some sort of total charge in the semiconductor given by this particular expression, right? So you can always find the point at which you have no further change in the current, right? So that you can do by saying that did by dvd to be 0. If I take this to see that when does the current maximize, for at what potential, drain potential, do have a maximum current, right? We take this expression and then differentiate it with respect to Vd and put to 0. We get what is called as Vd saturation. So Vd sat will turn out to be some potential at the length of the channel, some drain potential. is Vg minus Vfb minus 2 psi b plus root of epsilon s q Na by Cox square. So this is a rather long expression which shows that for any given Vg, there exists a point, there exists a drain potential where you have a maximum current, right? So now what happens beyond the maximum current is something that we will discuss soon enough. But then when we put this, we can see that you have a particular point at which the drain current maximizes, and it is that we call as the drain saturation current or drain saturation potential, right? So we use something like K, where K is given by root 2 epsilon s q Na by Cox. This is K, right? So if this is Vd sat, now what's the current at this particular saturation thing? Id sat is given by W by 2 ml mu n Cox Vg minus Vt square. Now we have reached to something which we have previously seen, where m is 1 plus k by 2 root psi b, and this m, so basically this m is a function of just doping, right? Because it is a function of k depends upon doping Na, and psi b is the potential which is required to invert the channel, right? And it is typically close to 1, and the ideal value when you get when you have very thin oxides and low doping densities, right? So this is some constant. And another thing that we have used here, which we have not defined yet, so this Vt is written as Vfb, so we define it here, right? Plus 2 psi b plus root of 2 epsilon s q Na. Remember, we defined the terminal or threshold voltage even in our metal oxide semiconductor junction, right? So at that point we had Vt is, which was written as Vfb plus 2 psi b plus q interface by Cox, and this is the total potential in the semiconductor. And this is something which comes because you remember we use this in our actual derivation, where here, right? So it comes from here. So it is the total potential at the semiconductor, right? Now this derivation of the threshold voltage can be inserted back into the total drain current, and we can see that when Vd is much smaller than Vg minus Vt, then the drain current turns out to be W by L mu n Cox Vg minus Vt minus Vd by 2 into Vd. And remember, this is the first term in the previous ID derivation, right? And secondly, when Vd is greater than Vd sat, remember Vd sat was the maximum point of it's the point of maximum current, as we saw before, right? When Vd is greater than Vd sat, we can see that the actual drain current does not depend upon the drain potential and is just given by W mu n C ox by 2 ml, and m was defined as we showed before, Vg minus Vt square. So the drain current depends majoritively only on the gate potential and not on the drain current, not on the drain potential. Yes. So any raise in the drain potential over and above the saturation uh, potential does not change the actual drain current. Now the physical reason behind this is that you have what is called as a pinch off, right? As we saw before, at this particular point the channel becomes pinched off in the sense that you lose the surface inversion very close to the drain and some regions, and any further increase in the drain potential only pushes the pinch off point further into the channel, right? So let's say we have our oxide, the gate metal, we have a source and drain. If Vg is greater than Vt, we have this is Qn of x, which we saw, right? And this is drain and source. Now if the drain is small enough such that if Vd is smaller than Vg minus Vt as we defined before, then we will have the same source and the drain, but then the channel slightly reduced near the drain side because of the fact that we have the drain source junction to be reverse biased, and we also saw the band structure where you see that the conduction band and the valence band are all lowered by the applied drain potential, and there can be a region in which the intrinsic energy level of the semiconductor bulk close to the drain slightly above the Fermi level, giving you a loss of inversion, right? Now if you have a very high for Vd much greater than Vg minus Vt, you have a source and the drain, and the channel becomes pinched off. This is Qn of x, source, this is oxide, and this is metal. Right? So and the depletion width here should look something like this, right? This entire region is the depletion width. And you can see that the channel is now seems to be of reduced width, and at each point here any increase in the drain potential will only push these things further, will push the pinch off region and closer to the source and away from the drain, right? And in between these two regions you have what is called as a non-linear region. In this region you have the ID expressed as W by L mu n C ox Vg minus Vt minus mVd by 2 Vd. So if I draw the entire this is ID written in the form of W mu n C ox by L, something like this for very low gate bias. You have the region of linearity, and you have a region where the current does not change any further after this particular point. So this is called as VD sat loci, and any region here where the current ID is linear with VD, so this is the linear region, and in between the linear and saturation region the current kind of tapers away, right? So this is the nonlinear region. In the nonlinear region, the charge density can be approximated by minus m del psi of y. Right? Now with this given, we will deal with one non-linearity or one non-ideality before we go and deal a little bit into the threshold voltages. One, it is called as velocity saturation. We already saw how we can include the oxide trap charges and stuff, right? So because which can be incorporated into the flat band voltage. We'll see what we can do about velocity saturation. Now the velocity saturation came when we assumed that the electron velocities in the x direction is constant with respect to the applied electric field, right? But then we know that this is not true for all conditions, and the velocity becomes field dependent, which is given by this expression. Where Vs is called as the saturation voltage, or it can also be approximated to be a saturation electric field. If I plot the electron velocity versus the electric field, we have assumed it to be linear for all velocities, but this is obviously not the case. So what happens is the velocity actually tapers after a particular electric field, and this tapering typically happens in two different things. This is for electron and this is for holes, and particularly there are two ways to handle this. It is what is called as piecewise linear approximation, where we say that the velocity is linear with the electric field up to some electric field EC called the critical field, above which the velocity kind of becomes constant, right? So this is called as a piecewise linear approximation. You can do this. So basically what happens is, we previously saw what is the IV characteristics when it is linear, right? So the second thing that we have to see is what happens to the ID current when you assume that the velocity is constant irrespective of the applied electric field. Under these situations, that is the second part of the approximation. In the piecewise velocity approximation, A linear till EC, this is something that we already saw. Then we see that after EC, the velocity is constant. It's just Vs. So under these situations, the current ID will turn out to be W by L Vs integral 0 to S Qn of x dx, right? And which will turn out to be W by L Vs into L Vg minus Vt into Cox. And so without going into detailed calculations of the drain current and the drain potential saturation, we will just see what happens if you include velocity saturation. The ideal case, when velocity saturation is not included, you have something like this. You have a linear region and you have the saturation beyond a particular point, right? So you have a linear region. This is Vd sat saturation and the nonlinear region. And you can see that as Vg increases, the gap sizes increases more. So basically you have a Gm which increases with Vg. We will do these exact calculations later on. In an ideal MOSFET, you have a Gm which increases with Vg, but whereas when you have velocity saturation into account, you will see that both Id and Vd sat reduces. So you have something like this. You have a linear region, you have a velocity saturation, and you will see that the drain current do not increase as much. Increases do not, the increase in, so this is Vg increase, right? So the drain current increase with Vg remains constant, in the sense that you have a constant Gm when velocity is saturated. You have Id sat and Vd sat smaller than ideal values under velocity saturation. Right. So with this treatment, we will stop today. The next time we meet, let us talk about current conduction when the channel is not inverted, that is sub-threshold conduction, because all the treatment that we saw today assumes that we calculate only the drift currents, so which assumes that you already have a velocity, you already have an inversion layer. Okay, with that, thank you and bye bye.